Hey everyone, welcome back to Math 256. This is Scott. Let's get started. So we're using a slightly different piece of technology today because the document camera that we usually use is out of commission. So I apologize if this doesn't look very good, but hopefully the problem will be short-lived as a new document camera is expected to arrive soon. But the show must go on. So let's talk about the subject of the day, which is the existence and uniqueness of solutions. All right, so here's the question. Under what conditions is a first order initial value problem guaranteed to have not just a solution, but a unique solution? And note about this, when we say a solution, that doesn't necessarily mean that we have the wherewithal to find the actual formula for it. And in fact, there may not even be a formula for it. But when we say a solution here, we mean a solution curve that is well defined. So i.e. a well-defined solution curve. Okay. So it doesn't have to be something that we can necessarily find analytically. It doesn't have to be something that we can boil down in terms of elementary formulas like sine, cosine, e to the x, or polynomials, but rather we're just asking in the abstract, when is there actually guaranteed to only be one solution curve that fits these criteria? And the answer is it depends on the nature of the differential equation. So answer. The differential equation has to have a smooth enough function to define it. Say defining it. Now that's not very precise, and mathematics is nothing if it is not precise. So let's actually put some more meat on those bones. So to make this more precise, we're going to have the existence and uniqueness theorem. All right, so this has a few moving parts, so let's just spell them all out. So here are the ingredients. So first off, let's say that we have the initial condition y of t naught equals y naught. So this is the initial condition. Okay, and then dy dt is equal to something that relates y and t, so in other words, a function of t and y. So this is a multivariable function. It has multiple variables in it, t and y. And specifically, there has to be a rectangle and we can define that by just using some interval notation here. So we'll say a to b cross c to d, where the t is in the first part. Sorry, t naught, I should say, is in the first part, and y naught is in the second part. So I'll draw a picture of this in a second so it can make more sense. Okay, so this is a rectangle. What about it? It's a rectangle specifically on which both f and the partial derivative of f with respect to y are both continuous. And remember what partial derivatives mean. So the partial of f with respect to y means the partial derivative where, or let's say with t treated as a constant. Okay, so in other words here, specifically, so graphically here, what we've got here, let's say this is the t-axis, this is the y-axis, and let's say this is t naught. Let's say this is y naught. So then our initial condition would put us right here on the y by t plane. And then in particular here, I called it a rectangle because if t is confined between a and b, and y is confined between c and d, then what we've got is essentially this little rectangle. This little rectangle here. This is R. So in other words, if you think about this in terms of, say, the slope field, what we've got is we've got a little part of the slope field surrounding our initial condition on which the function that defines our differential equation is continuous, and furthermore, its partial derivative with respect to y is also continuous. So that's what it means. That's what this means graphically. So then, if we have all of these pieces, then there is a unique solution which we'll call u of t such that, or u of t such that u prime of t is equal to f of t and y. So in other words, it satisfies the differential equation, and u of t naught is equal is equal to y naught on some interval of t values. And it's in particular an open interval of t values that contain this, so we'll call it e to f. All right, now again, this is all very very abstract. Let's actually look at this in practice, and it's more interesting first off to ask ourselves when this is not true rather than when it is true. So an interesting case of this not being satisfied would be a relatively simple differential equation like this. So let's say we took the differential equation dy dt is equal to, no, sorry, that's not right. I mean to say y to the 1/2, and let's just say y of 0 equals 0. All right, well, if we want to think about this, this differential equation here, this is a separable differential equation. In fact, actually, it's even autonomous, but specifically, it's separable, so we can solve it. And let's do that. Solve using separation of variables. So let's start by doing that. All right, well, if I separate the variables, I would get y to the negative 1/2 dy is equal to dt, and this would be accomplished by just doing essentially a little bit of cross multiplying / dividing. Multiply both sides by dt, divide both sides by y to the 1/2, or in other words, multiply by y to the negative 1/2, and then we can integrate. Which on the left side, we have a power function, which is nice and easy. You just add 1 to the power and divide by that. So in other words, it would now be y to the positive 1/2, and we divide by 1/2, which would be 2. And then on the right, what we would get is just going to be t plus just the first constant in the line here. We can just go ahead and solve that for the y by multiplying both sides by 1/2. So y to the 1/2 equals 1/2 t plus c2. So the next in our sequence of constants, where of course if we're being extra fastidious, we'll say that c2 equals 1/2 c1. But that's not a step that people usually are overly particular about. And then you just square both sides. And so then y would equal, at this point, so we're going to get 1/2 t plus c2 squared. But since this is actually the last in our sequence of calculations here, we can just call that a generic C rather than giving it any extra labeling. All right, so this is what the solution to the differential equation would be based on separating variables. If we wanted the initial value problem solution, then we need to actually plug in the initial condition, which was that y of 0 equals 0. And so then that's going to give us 0 for the y, and we plug in 0 for the t, and that gives us, of course, that c equals 0. Now, then what that means is that we are going to we're going to have the solution y of t is equal to 1/2, and it's just t plus 0 squared, or in other words, 1/2 t squared. And so then we could, if we want, simplify that a little bit to make 1/4 t squared. Okay, quick check here is that, so quick check, if we want to make sure about this, we can actually take the derivative. So then y prime of t would equal, you bring down the 2, so that would make 1/2 t, which is sure enough equal to the square root of, or in other words, the 1/2 power of. I'll write it in the style of the original differential equation. So that is also that is clearly the same thing as 1/4 t squared to the 1/2, which is equal to y to the 1/2. So yep, it checks out. The derivative does match what we have, and of course the initial condition would be satisfied. Okay, so that's all well and good. It went by the book. There was nothing too controversial in that, but I would like to bring your attention to a disturbing other fact here. There is another solution to this same initial value problem, which is not identical to this one. And let's just see what it is. So show that y identically equal to 0, so the constant function y equals 0, is also a solution. Well, not much to show here. Just seeing it, we can see that it's clearly true, and that's a disturbing fact because we thought we had solved it. And this is not the same as the solution we just got. Y constantly equal to 0 is not the same thing as y equals 1/4 t squared. So that's a disturbing phenomenon, but let's just make sure here. So if y equals 0, then y prime would also be equal to 0, which is sure enough the same thing as y to the 1/2. So yep, sure enough. And of course, y of 0 equals 0. Sure. Y of anything equals 0 according to this solution. So then the question is, what happened here? Why did this violate the theorem that we just said? One thing about mathematical theorems is they are the surest things in all of math. So why was this violated? So C. Which of the hypotheses of our theorem are violated? All right, so hypotheses of a theorem are the conditions under which it is true. So let's go ahead and look back at our ingredients and see which one was spoiled. All right, going up, going up, going up, going up. Okay, so here we have an initial condition. That's fine. We have a differential equation. That's fine as well. And we need to have a rectangle surrounding our point on which both f and the partial derivative of f with respect to y are continuous. So graphically here, we need to be able to surround our initial condition by a little rectangle where f is continuous and the partial derivative of f with respect to y are also continuous. So here, our f is equal to the y to the 1/2, and we will note that y to the 1/2 is the same as the square root of y, whose graph looks like this, and this is not continuous it's not continuous on any kind of window surrounding 0, because in fact it's not even defined to the left of 0. So this is not continuous on a actually I should say specifically here that the graph that we've just made here is a graph of f of y, or f with respect to y. So f is a function of both y and t, but in this case actually it was specifically only a function of y. So we can graph it with respect to y, and so our graph here is oriented a little differently from usual, but specifically the y now is this is so there is not an interval surrounding y naught for which this is true. On an interval surrounding y naught. And furthermore, and in fact actually, note the partial derivative of f is even worse. So here, partial derivative of f with respect to y is actually the same as just the regular derivative, because f does not have a dependence on t here. So this is equal to 1/2 y to the negative 1/2, which is in other words 1/2 times the square root of y, and this is not even defined at y equals 0. So this, which is not even defined. At y equals 0. So it's actually even worse. It's not only not continuous or on an interval surrounding it, it's not even defined at it. So, so the partial derivative of f with respect to y is very very bad as far as the conditions of the theorem go. All right. Let's look at another example here, and the other example would be another differential equation, again separable, because those are the easiest of our categories of differential equations to handle, provided that the integration is not so bad. Let's take one like this. dy dt is equal to 1 over t plus 1 times y minus 1. And we need an initial condition, and we'll just say y of 0 is equal to -1. Okay, so let's just take this, and we will just try to solve it first and then ask some questions. So first off, solve the initial value problem. All right. So let's just see what the algebra and calculus would lead us to for this one. So we do the usual do-si-do, and we get y minus 1 dy on the left, and on the right we have, we just multiply by dt. We have 1 over t plus 1 dt. And then we make those into integrals, and we go from there. Now on the left, we're going to do like we did before. Since our ultimate goal here is going to be to solve for y, it would be useful for us to have to treat this whole thing as a u substitution. It could also be integrated term by term, but that's going to complicate our lives when we want to try to solve for y, because we'd have a y squared and also a y, so it'd be quadratic in y. So it'd be better if we have something all squared. So again, we can think of this as a u substitution with u equals y minus 1. And in any case, what that's going to get us is 1/2 y minus 1 squared. You can think of this as being u equals y minus 1, which means that du would equal dy. If you want there to be something, there to be a paper trail here, that's what it might look like. Again, this can be done term by term. It just won't be easy to solve for y, whereas what we have here should be easy to solve for y. On this other one, it's again kind of it's a u substitution where u equals t plus 1, meaning du equals dt. And so we've got 1 over u. So in other words, we have the natural log of u, of absolute value of u, of course, which is equal to natural log of t plus 1. And now we have our constant of integration. We have, as usual, consolidated the constants of integration all to the right. And then we want to solve this for the y, so I multiply both sides by 2. And let's see what we have now. So it's another constant. I keep promising that someday I'll stop writing these little commentaries on the constants, but hasn't happened yet. All right, now I will take the square root of both sides. And actually, when I'm taking the square root of both sides here, it's interesting to note that that in reality here we've got a plus minus situation when we are solving this. So I might go ahead and put that in just because you never know when you have to keep these things in consideration, and it's always good to err on the side of caution. So this is all to the 1/2. And then that means that y is equal to 1 plus or minus the square root of, or the 1/2 power of, 2 natural log t plus 1 absolute value plus c2 to the 1/2. And now to figure out the rest of it, we just need to take into account the initial condition y of 0 equals -1. So that'll help us find the c. It'll also help us decide between the plus and the minus. So first off, so -1 equals 1, and it's either going to be plus or minus, but note that the square root of any real number is going to be non-negative. So therefore, what we have here is not going to be the plus; it's going to be the minus. So here, so it must be negative. Otherwise, this isn't going to work. You can't take a square root of something and get of a real number and get a negative result, and so therefore we're not going to be producing the 1 plus anything over here to make -1. Okay, so then that is going to be 2 natural log. You plug in 0 for t, so that's just going to be natural log of 1 plus c. And I guess I called it a c2, but I can drop that pretense now, or I can just leave it in. Might as well, since I forgot to drop it. I'll just continue to have it. So then here we remember our rules of logarithms, and remember that the natural log of 1 is equal to 0. So this is equal to 1 minus just 0 plus c2. And now to solve this, we would just subtract 1 from both sides and multiply both sides by -1, let's say, or alternatively add c2 to the c2 term to both sides, and add 1 to both sides. So then I would square both sides and get c2 is equal to 4. Okay, well then, that means that our solution is y is equal to 1 minus, and we didn't know if it was going to be plus or minus. That was a thing that the initial condition was actually going to have to determine for us. 2 times the natural log of t plus 1 absolute value plus 4, all to the 1/2. All right, so now we have a solution, and we can ask ourselves here, based on this solution, we can ask ourselves about the interval of existence on this. So as long as this solution is defined, it's going to be a good solution. We found it analytically. And we can just try to figure out when is this even going to be defined. So so that'll be our part B for our question here. So, so part B, use. So use your solution to determine the interval of convergence. All right. Well, we just have to ask ourselves, when is this even going to be? When is this going to be defined? What's gonna be a possible issue for it? And when are we going to be in the clear? So essentially, for our existence, I should say, not convergence. Interval of convergence. That's of course a phrase that it comes up in Math 253. Here we mean existence. And so let's just actually see when is this actually even going to be defined. So in order for this to exist, we need the answer to be a real number. And if we look at this, we've got a square root of a number. So note 2 natural log of t plus 1 plus 4 has to be greater than or equal to 0 for the value to exist. Okay, so then what's that mean? That means that 2 natural log of t plus 1 has to be greater than or equal to -4 And then if I divide both sides by 2, that's going to give me the natural log, absolute value, t plus 1 is greater than or equal to -2, which if you remember, natural logs do produce negative answers if the input is less than 1. So in particular here, we can use the exponential function, which is a monotonically increasing function, just a note, which means that it will preserve any inequality. If you put in a bigger number, you get out a bigger number. So therefore, we have the absolute value of t plus 1 is greater than or equal to e to the -2. And what that then means, so this is increasing. And an increasing function, by its very definition, means that if you plug in a bigger input, you get a bigger output. And that's how we can preserve this inequality this way. Okay, and then what that means is that basically we need t plus 1 to be either more negative than negative this, or more positive than positive that. So that means this is either less than or equal to e to the negative e to the -2, or t plus 1 is greater than or equal to e to the -2. So we've determined that the inequality has to be, or the absolute value has to be greater than this number, which means it's either more negative or more positive than the negative version of this or the positive version of this. Which then means that t is less than or equal to -1, -1 minus e to the -2, or t is greater than or equal to e to the -2 minus 1. So essentially, you solve each of these, and since here we know that our initial t value was t equals 0. That means that we must be talking about the one that is greater than this. So e to the -2 is less than 1, just a note. And since t naught is equal to 0, we can't have t less than or equal to -1 minus e to the -2. So we must have t greater than or equal to e to the -2 minus 1, which as a note means that we are talking about a specific number here. I'll plug it into a calculator and see what we get. So this is t greater than about 0.865. So t is greater than or equal to 0.865. Oops, 8. Approximately. So then the interval of existence is t is that we're talking about essentially the open-ended interval that goes from from e to the -2 minus 1 to infinity. Okay, so now let's have a look at what some of these differential equations look like and see if we can try to figure out visually what all of this means. All right, everyone, here I have just Googled Bluffton differential equations because it's a nice little program that gives us very easy access to slope fields and solution curves. So let's try to get a look at what we have just been exploring. So we're going to put the same differential equations in as what we were dealing with, and we can even customize the variables to be the ones that match the ones that we have been playing with. And now let's go ahead and put in y to the 1/2 as our differential equation. All right, and notice, by the way, that the entire lower half of the yt plane is missing because this is obviously not going to be defined when y is going to be negative. That's the reason for that, and we'll put y starting at 0 here just to make that a little clearer. And now let's put in a numerical solution curve. We'll use the Runge-Kutta, so make the best possible curve. And let's just put in y equals like 0 and 0 for the y and the t. All right, it just put it right along the bottom there. Not a big surprise. If you plug in y equals 0, you're going to get a slope of 0, which is going to lead to the next point being at the same y value, which is 0, which will then just repeat the whole process over and over and over again. Now it also just so happens to be the case that the other functions that we found as solutions, those fit just as well. So if we plot for other functions here, let's say we put in 1/4 t squared. I guess it wants it to be an x when on this field. Notice that at least when x is when the t is greater than or equal to 0, this fits just fine. It doesn't fit so well on the other side, as you can see. The reason for that is that that's where we hit the discontinuity, and an initial condition that put us back on that side of things would have ended up not quite fitting so well. So if we cut our t off at 0 here to match our particular initial condition, you can see that both of these curves seem fine. The one at y equals 0, we can't really see the slope field that well down at that level, but we can certainly, I think, believe that if we could see those line segments, they would yeah. So we can see along the y-axis here, or along the t-axis, that it's basically flat. So the reason why our theorem is violated here is the fact that basically we have a singularity at at 0, 0. In particular, at y equals 0, just that function or just that value. That is a place where we cannot have the amount of continuity that we expect to have, according to the hypotheses of the existence and uniqueness theorem. By the way, if you haven't ever played around with Bluffton, one of the most fun things is you can really make a visually striking graph by just clicking around a bunch and putting in a bunch of solution curves, and it looks very pretty. But enough for that. Now let's look at the other differential equation. So we'll clear all of our curves. Also, we'll get rid of this other function here. And we will put in the other differential equation, which was 1 divided by, and now what did we have? We had t plus 1. And then y minus 1. Okay, so you can see here we got some interesting stuff going on. I'm going to change our window back to the default of -3 to 3 and -4 to 4. And notice some very peculiar features on this particular graph. And if we put in the initial conditions that we had, y of 0 equals -1, so that means we're going to have a -1 here. You can see that we have a curve that looks very peculiar indeed. So this is a very strange looking one, and then when it comes to where we are, where our solution here, where it continues to be defined, basically the place where it is vertical right here is essentially going to be the t-value that we identified. So I'm going to make this a little bit narrower of a window here so that we can see it better. And we'll make it like that. And if we look at it here, the spot where we end up with this little singularity where it goes vertical in this particular function is going to correspond to that 0.8 to that 0.864 thing that we saw. And then other than that, we get a more jagged curve than we're used to seeing from Rumakuda, but that's just because we zoomed in so much. So let's go ahead and give ourselves a little bit smaller step size, and notice the weirdness here. So here is the weirdness that comes at that one particular value on the edge of our interval of existence. It ends up spiking off in a weird way, and that just has to do with the fact that natural logs, as you start plugging in something that becomes less and less say friendly, give us farther and farther and farther extreme numbers. And also if we look at it a bit bigger picture here, there are oops, what am I saying? I meant that to be -3 to +3. So if we look bigger picture here, we can see that we have some clear issues at -1 itself, especially when the y also equals 1, and that's not to be too surprising because those are, of course, the problem values in our original differential equation. So that's where things stand with this. So let's go ahead and wrap that up now and call that a lesson. So this has been your episode of Math 256 for section 1.6. I'll see you for the next one. Bye.